Check. Hello out there. Good. Okay. Let's let a few more people join the stream. And then we'll get started. Hopefully it's not laggy here. Right now it's only showing me 3 people tuned in. Not sure if 1 or 2 people dropped out briefly. How many people do we have on the Discord? Of course, just because people have green dots does not necessarily mean they're planning on watching live. Oh, there, the number count just bumped up to 5. That's about normal, I think. All right, so I'm gonna go ahead and get started, and let's just dive into this, shall we? So what I want to talk about tonight are the things you're going to need to know for the final project. And after this, I'd say, let's see, do we have 2 weeks or 1 week of actual classes? I guess. Yeah, so next week is the last week of regular classes. The week after that is officially finals week. I will do the live sessions next week, but they're basically just going to be question and answer. I'll talk about, depending on what anybody has to ask, I'll talk about something, but if nobody really has any questions, those might be really short. So at any rate, for tonight, what I want to do is make sure you know what you need to know to do the final project. Now, you might be able to just piece it together from the instructions. They're pretty complete, but this will help orient you a bit more and probably save you some time to have attended this session or to watch this video later. So first, let's actually just go to the lab instructions here, and I just want to walk through the instructions for the final lab. And I think I showed you guys this couple 3 weeks ago briefly. And what this lab is about is making an AssemblyPede game, and it's even got a little video here that shows you what that game looks like in miniature, and we're actually going to see that live in just a moment. So I'm just going to pause that. So the idea here is you've got a program to download, and then the other 3 files are just level files. They just make the map that the centipede is running around in. So the one that's really important is the AssemblyPede file, but you should get the level files just as examples. One of the things you'll do is create your own level file, which is just a, you edit text with a text editor, you got a level file, basically. And the idea here is that it's not quite complete, and you're going to fix a couple minor glitches and add some features to it. And I wanted to do the project like this because it lets you see a more substantial assembly language program. You may pick up ideas and tricks and ways to think about things just by seeing how this program works and figuring it out enough to actually then modify it and fix it or add features. So I think it'll be a good learning experience. And I'm always more interested in a learning experience than whether it tests you, but this is going to be a challenge as well. So I think it fits all the criterion it needs to for a final project. So basically, once you do this, you will turn in your own version of that program, and you should also turn in, whoops, I named these wrong in the instructions. You'll also turn in your own version of 1 or more level files. That's just mainly to encourage you to just have a little fun and be creative. Design your own level for the game. Let's see. If you got some things working and then try to get some other things working but don't quite finish it, what you should turn in is turn in your latest working version and your latest attempt, or even maybe more than one attempt. Things that didn't work, but you gave it a try. You want me to see what code you wrote, as it might get you some partial credit or something like that. So, and then of course you should turn in some screenshots that show pretty thorough testing of your program. So that's the essence of what you're going to do for this. Now there are a few things we're going to need to kind of walk through. One is the program itself uses a thing called the ncurses library, which, much like the standard C library, it's a library you can get you can install on your Linux system, and then it has a bunch of functions defined that you can use. And they're C functions, but as we already know, we can call C functions from assembly language programs, and so I chose to use this library just because it lets me do slightly more fun things. It's what enables the animation that you see here. So even without user input, this thing moves around at a kind of a constant velocity. And one of the functions provided by the ncurses library is the most convenient for that. It provides a few other functions that are kind of handy as well. And the ncurses library is actually something that I would encourage you all to play around with. It's basically a library that lets you work with text, as in a terminal, but it lets you control things like colors and control things like, you can move the cursor to where you want to print the text anywhere on the screen, that sort of thing. It gives you ways of clearing and redrawing the screens, and that's kind of what allows you to do animation and so forth. So I would certainly encourage you to play around with that, learn a little bit about it. It's something that you can use to make C programming that you might do in other classes in the future a little bit more fun, or it's simple enough to work with that if you watch a couple hour tutorials, you could be writing, you know, some simple fun games. You could be writing a game not much less complicated or interesting than this AssemblyLanguage game and so forth. So at any rate, it's just something fun to play around with. So outside of this lab, I encourage you to learn more about it. So we're going to get that installed, and then we'll use it to build the game and run the game, and you'll see that shortly. Now, once you have the game and have it working and are able to build and run it as is, I think your next thing is going to be to study that game, study the program itself to understand how it works, and that way you'll be able to then make modifications as needed. So the modifications you're going to make are listed here, and the required fixes, these are the things I want you to do. That if you just do all these things and that's it, that would be, you know, 100% credit. But I leave the door wide open to do extra credit. And even if you don't think you need extra credit, I encourage you to pick some of this stuff out and just do some stuff for fun if you've got the time. Because I think there's a lot of things you could do with this that would be a lot of fun. So I encourage you to have fun with it most of all. But the kinds of things you'll be doing, one thing is, again, create your own level file. That's really just a text file you edit in a text editor, so that's pretty easy to do. Couple glitches to fix. One is don't allow the AssemblyLanguage worm to move off the level map, which currently it can do, and it can crash the program if you let it go too far off the map. Because it actually starts writing things into memory areas that it's not supposed to write to. And let's see, at the beginning of the game, well, I think when I show you the game, I'll talk about that in more detail. But so there's a few glitches to fix. Then, you know, things like, okay, well, if the user presses spacebar, pause the game and show them the instructions for the game or something like that. And then if they hit the spacebar again, it resumes the game. Or they can use a Q to quit. Right now, the AssemblyLanguage can't die. It just moves around anywhere at once and does not actually ever die. So one of the things to add to the game is the fact that when it hits the wrong kind of thing, like if it runs into itself or runs into a wall, it should die. So you need to add that. The AssemblyLanguage is supposed to grow as it eats food in the level. Asterisks are food, and it's supposed to grow. So that's another thing that you would need to add to the game. Showing a score, basically showing how many food it has eaten. And the final feature would be to add a portal to the game, which sounds a lot more mysterious than it is. Once you put some thought into it and understand how everything else works, the portal is actually not that difficult. So those are the things that you would actually need to do to add to this program. And then there's lots of extra credit options listed here. And these are just things that I've thought of that I thought might be fun. And you're welcome to think of any modification to this game you think would be fun, or if you look at the way the game does the animation and you want to write a whole new game, like you have tons of time, feel free, write a whole new game. You know, something that's completely different. I think that would be pretty cool if somebody wanted to turn something in like that. So that's the essence of what this final lab is. So now let me go over to our virtual machine and let's talk about downloading these files. The easiest way to download them is probably to use this link. This is the web link to our OneNote notebook, so you can get right back here, but do it in a web browser. And what I would do is I would copy this link. So copy link right here. And then in your virtual machine, I would bring up Firefox. So I don't know if any of you have used Firefox from within your virtual machine, but you should have a button down on your toolbar. If not, you should be able to find Firefox over here in the menu. But run Firefox from your virtual machine. Of course, this does mean your virtual machine needs internet access. Normally, it will have internet if your host machine has internet, so that hopefully will not be an issue. I don't think it's been an issue for anybody so far. But every once in a while, your virtual machine might lose. Whoops! Why am I not getting a paste there? Let me try that again. Copy link, come back to my VM and paste. There we go. So I just pasted the link in. So if we do that, we should get to our OneNote notebook and click the labs and come down to lab OXFF. And then from here, you can just download the files straight to your virtual machine. You don't have to worry about copying and pasting or how you share files between your host machine and your virtual machine. There is actually a way to create a shared folder that your virtual machine shares with your host machine. It's not too hard to figure out if you want to Google that as a way to do that. Of course, it's kind of late in the game. If you probably either already figured that out for yourself or you have your own ways of moving things around. But if you want to download these files, and this also applies to the files in Lab 7, you can come here from within Firefox, within your virtual machine, and then if you download these, they just go straight to your virtual machine. And so I'm doing this. I've already done this, so I'm probably getting them renamed or something, but so there we go. I've just done that. And I would suggest if you're able to watch the video and do what I'm doing as I'm talking, then certainly go ahead and do that and try to keep up. So let's go ahead and take a look at what I just downloaded. So I'm bringing up a terminal here. And let's cd to my downloads folder. So I'll go to my home folder, downloads, ls, and yeah, I have duplicates of these things. So here's the AssemblyPed and 3 level files. So those are just plain text files. We'll take a look at those in a moment. But I've already moved copies of these over into my work folder. So let me go back there. And I actually made one specifically for this lab. And I would recommend setting off a new folder just for this lab. Probably a folder for each lab by itself, which you're probably already doing. So I don't know why I'm telling you the obvious. Okay, so here is my folder. Now, I've already been testing this to make sure everything was working properly before I talked about this with y'all. But let me go ahead and delete the things that have been built. Let's see. Okay, so there's the 4 files downloaded. All right. Just real quick, let's take a look at a level file. Let's look at just the basic level file, levelfile.txt, and I'll explain the file format of the level files. So gedit levelfile.txt and bring that up in the gedit. All right, so this is a level file, and you can see it's pretty simple. It's just plain text. And here I'm just using plus signs and dashes and vertical bars for walls, and I only have outside walls, no maze or rooms or anything in this file. And then there's the asterisks that represent food for the AssemblyPed to eat, right? And now notice that the file starts with the dimensions. Okay, so it's 42 wide and 24 tall. So that's width and height. So if we actually count here, you'll see that if you look at the column number it shows here, that'll be, it's saying 43 because I have the cursor after the 42nd column. So if I put the cursor here, notice it says column 1. So if I put the cursor before that plus, you'll see it's column 42. So you're seeing that I've made my level 42 wide, and if you count the rows here, it's 24 lines high. So that's the first thing you do, is set the height or the width and the height. Then you just draw your level in text. Now, one important thing is you don't want to have any extra spaces. On your lines here, okay, or other characters. So whatever width you specify, so if you specify a width of 42, you only want exactly 42 characters and nothing else. No invisible spaces or anything else. So that's the basics of the level file. Then all there is here after that, this is actually telling where the assemblypede, the worm, so to speak, this lays out where that is to start off. So it says how many body segments it has, and then you have where's the head, and then each body segment. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's, I was trying to remember if I was counting the head as body segment, but I guess I am. So you have basically 12 body segments. The first one is the head. And so these are the coordinates of that body segment. And in this case, it's counting, it's X and Y coordinates basically, but Y counts down. So it's how many columns over and how many rows down are the way these coordinates are given. And so if we think about it, 10, 10 would mean it'll be on, well, line 2 would be row 1. Actually, I'm not sure. Actually, it'd be 0 base, so this would be row 0. So if we go to row 10 from there, I believe, if I'm doing the math in my head right, that should be row 12, or at least it's close enough. And so if we find column 10, which would be right about here, that means the head of the assemblypede will be there, and then we see that the next body segment is there at 9, 10, and then 8, 10 there, and I might be slightly off here, but, and then I think if you read these numbers off, then 8, 8, 8, 9, 8, 7, this is where the assemblypede bodies are going to be. Now I have my reasons. There's sort of reasons why I did the body where you put in the coordinates of the initial body segments and the head, but because if I had drawn it in, like if the initial level, if you just were allowed to just say, okay, this is where, oops, maybe you would want to just draw it into your level file like this and just have, okay, the program's going to read the level file and it's going to figure out where the worm is based on where it sees the O's and the @ signs. The thing there is it's kind of difficult to establish as you read these O's, you know, is this the last body segment or is this the second to last body segment? Is it in the middle somewhere? If it's going to turn, where are you in the body? It would actually take, certainly not impossible, but it would make the code a lot more complicated to actually have to find where the @ sign is in the input, and then to figure out what the sequence of coordinates of the body segments are. So rather than do that, the level file just makes it simpler by explicitly putting in the coordinates of the body segments in their sequence. So that's what a level file looks like, and I might as well open this one because it's just a little more interesting. So this is a slightly more interesting level file because it has a room here and kind of obstacles. So if the assemblypede is moving fairly fast, it's a little tricky to get in here and eat all this food and get back out, especially when your own body blocks you from one door and you maybe have to go out the other door because the assemblypede has gotten so big at that point. So it just gives you an idea. So, and the idea here is that the program will be given which level file to read to play the game, so you can actually play the game with several different level files. So that's what the level files are about. Feel free to pop in and ask any questions, but I think that's pretty straightforward, so I'm not really expecting questions. Here is the assemblypede program itself. Before I do that, let me go back to my notes and make sure I'm on track with everything I want to talk about. Okay, so I showed you how to download the files, so I haven't actually built and run it, so let's get back to that track. So I mentioned that it needs ncurses, so let's walk through installing ncurses and then building and running the program. Now here in the notes I have given a bunch of links to information about ncurses. Now you can start with the Wikipedia page just to kind of get an overview of what ncurses actually is. But I've linked to a few online tutorials that are pretty good, and if it's something you're having fun with, and again, if you have time, don't make if it is something fun, make sure you have time and you don't cost your other classes or things getting into it. But if you enjoy it, there is a one of these links goes to a web tutorial.
Another tutorial series. In this one,
which is pretty good. It builds up a roguelike game, if you know what those are. If not, Google them. That would walk you through a pretty elaborate game creation tutorial. So you spend a few hours doing that. You learn a lot, not just ncurses, but you learn a lot of programming techniques. You learn some good stuff. And that would be doing it in C. Of course, ncurses is a C library. We're using assembly language, but we know how to call C functions from assembly language now, so we can use it for our stuff. And we're not really using much of ncurses. I'm only using it to make it easy to clear and redraw the screen and to have animation based on clock ticks. That's really about the only two reasons I'm using the ncurses functions here. But you could certainly, if you wanted to learn more ncurses, you could add color to this and do all kinds of fun stuff. So so we're gonna install ncurses, which is pretty easy to do. You've already installed quite a few things into your Linux machine. So step one, usually when you're gonna do a apt-get install, first you should do update, so it updates its own information of what is available out there to install. So we'll do that first. And once that update command is run, I've run it fairly recently, so it went fast for me. You might have yours take 60 seconds or 2 minutes maybe to finish. Once you've got that, then we want to install. Let's see if I can just arrow up to where I had it before. Then we want to install lib32 ncurses. You want most of you went along with me as far as installing 64-bit Linux Mint, even though we're doing 32-bit programs with our assembly language programs. So for this to work, you need the 32-bit version of the ncurses library. So for that, install this. You want sudo apt-get install lib32 ncurses 5-dev. I think there's actually a version 6 out there now, but I'm just sticking with what I already know works with what I have. Probably the latest version of ncurses would work fine if you want to Google and find which package name to download for that. It might be as simple as changing that 5 to a 6. But I don't want to get off track and have some error mysterious error pop up and have things not work and have to figure that out. So if you stick with this, you should be good to go. So let that install, and yours may or may not ask you, are you sure you want to install it? I think it didn't ask me this because I've already installed it and removed it once, although I'm not sure why it shouldn't still confirm, but it didn't. With that, you should have what you need. It's possible there might be another package, so when you follow along with me and try to build it, if you get an error message with the linker, let me know, and I'll let you know. Maybe we also do need to bring in the 64-bit ncurses package, but I don't think we do. So once you've got ncurses installed, then you can actually build and then run the AssemblyPed program. So if we come back over to the instructions, so, and these commands are right here in the instructions, so I don't think we need to do this one, which is just this regular lib ncurses package. That would bring in the 64-bit ncurses, but we might. We'll see how it goes. I actually already have this one installed on my machine, so but I'm not sure that you need it. Can't hurt to install it, so you might as well run this sudo command right here as well. And then we want to run this nasm command right here, which is pretty much our standard nasm command that we always do, just on the AssemblyPed program. So let's go ahead and do that. So nasm -f elf32 assemblyped.asm, and runs without a hitch. And let's see. And then the last thing you want is the linker command, which is right here. Which I'm just going to paste in. And one thing it's going to do is it's giving us this gets. When I wrote this program a year ago, I had this left in there. This actually does not hurt anything, but it's a one-line delete that we can get rid of what's causing this warning. So I'll show you that, and you can just edit it in your own copy of the file. But it is now built, and so it's time to run it. So /assemblyped. And boom, what does it do? It tells me that, hey, we need a level file name. So this is a program that uses a command line argument. Now, a few sessions ago, I did show you how to do command line arguments, or how to find the command line arguments in an assembly language program. And actually the comments in the AssemblyPed program itself, when we get in there, you'll see that it actually shows you how to find those arguments as well. So this would be another example of how you can do that. So we need to give it a command line argument, so AssemblyPed, and then we need to give it the level file name. So let's start with that original level file, the simple one, like so. And now it will read that level file, load it up, and then run the game. And there we go. The game is actually taking up a little bit of space. And you'll notice something a little quirky happened there. That's one of the things you're supposed to fix as part of this project. But right now you can see the AssemblyPed head is just sitting there frozen, and it'll stay there until I actually hit a W, A, S, or D movement key. So I'll hit D here, and there it starts moving. And then that tail regrows. The tail, I'll start it again and watch it, or if you are following along with me, run it on your own computer so you can see what happens. And I also have intentionally set the speed fairly slow so it's not too hard to mess around. You can, of course, decide that you want your game to go a bit faster than this, and so that's one of the things you can go in and tweak in the program. So now let me let it hit a star, and you'll see that it eats the food. But what it doesn't do is grow. You'll notice that it's staying exactly the same length all the time. It's a little bit hard to count body segments while it's moving, but it doesn't grow. And that's one of the other features that you'll be responsible for implementing, is that each time it runs over one of these asterisks, the body should get longer by one body segment. And another thing that doesn't happen is when I clear all the food, it doesn't end the level or anything. It just keeps going. So that would be another feature to add. Have the level end. And another thing that doesn't happen, watch what happens when I make it run into itself. It just crosses right over itself. It's perfectly happy. For a moment, the overlapping body segments sort of erase each other. And also watch what happens if I go off the edge. It starts to screw up the map a little bit. Basically, I ended up deleting a new line character there, so one of the lines of the map is now in a weird position, and now another one is, and if we go off one of the top or bottom edges, that's where we're going to eventually go outside the memory buffer that represents the map and hit memory that we shouldn't be trying to print @ and O's into. So if I just let this go for a while, we should get a segmentation fault here eventually. Not sure how long it'll take. I didn't test going this direction. There we go. So that is an example of running the game. And again, the idea with the level files is you can give it different level files. And one thing you'll find, running the game may kind of mess up your terminal if you click reset, or maybe even reset and clear here in the terminal menu. That should bring things back to normal. Let's see, what was my other level? Yeah, this is the one with the room. And notice, did you catch that? I'm gonna stop it. Pay attention here. Watch what happens to the worm right when the game starts. Watch where the worm is and what happens. See how the body segments, like its tail is shrinking or its body just shrank into its head. That's one of the fixes to add, is to see why that's happening and fix it so it doesn't happen. And notice that it kind of grows back to that original length after I start moving. So we can run around and eat food, but notice I can run right through walls and destroy walls right now, where really the assembly should die when that happens. But anyway, there you go. That is another level file. And we'll talk about the third level file. We'll talk about that in a moment. That's something to give it a little bit better of a visual feel if you want to play around with it, but it's not really required. So let me check my notes again and just see what else I want to say. Make sure I'm staying on track. Okay, so I've kind of already given you the overview of what ncurses is, and I encourage you to follow these links or just Google ncurses documentation, ncurses tutorials, see what you find that works for you if you want to learn more about it. Now I will say that anything you find about ncurses is going to be in the context of writing a C program with that library, but again, since you know how to call C functions in assembly, all you really need to do is understand what the ncurses functions do and how to use them, and then you can use them in a C program or use them in an assembly program. Either is just as good. Okay, so we've seen how to build and run it. So far so good. Let me make sure I have the chat up in case anybody's asking questions. Where'd that go? There it is. All right, doesn't seem to be any questions. Let's see. So I've already gone over the level file format, so we may not have a whole lot more to talk about other than actually diving into the program and seeing how it works. But I do want to show you, yeah, I guess this is a good time to talk about that third level file and what that does. So let's jump back over to the to my virtual machine here. And first let me reset something. All right, so normally your terminal will have what's called a character encoding, which is basically how it takes 1-byte characters, ASCII characters, and how it actually interprets them as text. And the actual default here is what's called UTF-8, which is basically the ASCII code. UTF, that's the 1-byte universal text format. I think that's what the UTF stands for, or the Unicode text format. But it's based on ASCII, so the simplest version of Unicode is basically the ASCII code. So that's the 1-byte version of Unicode. When you extend the Unicode to 2 bytes or more than 2 bytes, then that's when you get all alphabets from just about every language ever, as well as a lot of emoticons and all that sort of stuff are encoded there, I think. That is what these terminals are normally using. But if you switch to this Western IBM 850, and if anybody's trying to follow along with me, you should have a question right now, which is, I don't see that. So is anybody following along with me and not seeing this option under character sets? And if you're not, well, just drop down to this add or remove. And this is how we can add it in there. So if you do add and remove here, and you find this encodings list, just scroll through this mess until you find IBM 850 Western. That's the coding that I'm using for this other level file. I think sometimes it just gets laggy as far as the video feed. But if you can select the IBM 850 there and have a checkbox on it, then close that. Then when you come back up here to the terminal, you should have it listed. And if you select that one, actually let's see what that file looks like if we don't select that. So keep it on Unicode first. So put it on that default Unicode. And I'm just gonna let's just look at the level files. Like you can just cat level file.txt, whoops, and take a look at, okay, there's what that level file looks like. I'm gonna zoom my terminal out a little bit just so I can see more stuff at once. And now let's, what are my other file names there? So now let's look at that IBM 850.txt. So cat level 1 IBM 850.txt. And look at this mess. We got all these weird hexagons with question marks in them, which basically means you got some character codes in there that are not recognized under UTF-8. Okay? But they would be recognized if we switch to IBM 850. And so switching to that, and then catting that set of characters again, boom. Look at that. You have these nice looking walls with nice corners and all that kind of stuff. So that's just a different character set that you can play with. And now you might not know what key to press to get one of these corners, but you can always just copy and paste, right? But if you're going to actually mess with this, you would want to do that in gedit. So now let me show you how to do this, mess with this in gedit. So if we open up that IBM file, now if you open it up, it's not going to look like this, and that's because you have to choose the character set you want to open it up with. So I'm going to reopen this one. I'm going to close it here. Whoops. Okay, there we go. So I'm going to go to Open, and I'm going to find that thing. Here's my level 1 IBM 850.txt file, and I'm going to open that, but I'm just going to let it automatically choose the character set, and it's not going to choose the right one. So there, again, it's printing, it looks like it's a bunch of weird codes. Actually, it's showing us different things than the terminal did, but it's the same byte codes, it's the same numerical codes for those bytes, but it's just a question of how gedit wants to display it, how the terminal wants to display it, and so forth. So instead of opening it that way, let's close it again, and now let's do a file open, and it's in the file open where you choose the character set. And so once again, you want to find the IBM 850, Western IBM 850. That's the character set you want. And of course, that's not going to be listed by default, so you have to choose Add or Remove and find it first. So if you find the one you want, well, here I will deliberately remove it. Okay, so now if I come to my character set selection here, I don't have IBM 850 to add in, right? So now I have to click Add and Remove, and then I have to find IBM 850, and I think it's way down here near the bottom. Yeah, it's like the second to last one. All right, there it is, and then you click the little plus there, and then it adds over to the list on this side, and click Apply, and now you can choose it in this list. Choose IBM 850 as the character set, and choose the file you want to open with that interpretation, and click Open, and now you see the characters like this. So you could play with this. You could also look up other character sets that you think look better if you wanted to mess around with that. This is just something, it doesn't hurt to know that these things called character sets exist. They're different ways of visually interpreting the various 1-byte codes. Now the ASCII code is pretty standard, but that actually only goes up to 127. So from 128 on up to 255, those are a lot of variations that are called extended ASCII codes. So UTF-8 has its interpretation and so forth. Let's see. So if you wanted to do this and edit it, you can always, just select one character, copy, paste that character. Of course, then you maybe have to delete to line things up again. So if you wanted to build a wall over here, you can just start editing like this and just pasting the walls in. If you wanted a horizontal wall, that's a bit easier. You could just copy some section of the top or bottom, and there you've got a horizontal wall. Of course, then this got shifted over, so bring it back, and so forth. So if you like the look of these walls a bit better, you can mess around with the character set and have better looking walls. But if you're okay with pluses and dashes, then pluses and dashes it is. So I just wanted to show you that as something to play with. And the other thing you might want to do, that's definitely not in the required features, but you might want to look up how ncurses controls color. It might be a little bit nicer if your walls and your food and your assemblypede and anything else you put in the game can have different colors so they stand out from each other a little bit more. So you can look up in ncurses and see if you can figure out how to control colors. Let's see. That actually might be, it might be a little bit more difficult to control colors than I'm making it sound, though, just the way I have the level set up. So keep that in mind. It might turn out to be harder than it sounds. All right, so that's level files, that's character sets, if you want to play with that. And let's move on then and talk about how this program actually works. And I'm just going to try and give you an overview. I mean, basically, the essence of this assignment is reading the code yourself to really grasp what's going on. But you know, I will answer emails. So after you study the code and you say, oh, I don't understand how this part of the program works, or why you use this instruction here, or you know, you can ask me plenty of questions. But I will give you an overview right now, so that hopefully you'll be well oriented to get started. So let's go ahead and look at the AssemblyLanguage program. All right, now one thing, I've done my data section and my BSS section first. That doesn't change anything. It just, you can do it that way if you want, basically. And you'll notice that the externs and globals and so forth do not actually have to be defined within section.text. That just happens to be where we've been putting them kind of habitually. But here, it's just kind of out. Actually, technically, I guess it's inside the BSS section, but it doesn't really mean anything which quote-unquote section these things go in. So the first thing I'll show you right here is, so these are all the standard C library functions I'm using. Notice quite a few more than we've been using, but there's your printf, and I'm using fscanf instead of scanf. So that's scanf to read from a data file, not to read from terminal input. And similarly, we have the fgets, and then there's fopen and fclose. Those are functions specifically to open a data file and close a data file. So again, since we're getting a file name on the command line, right? So we give a file name here on the command line when we run the program. That file name comes in. The program's actually going to use that file name. It's going to use fopen to open the file. It's going to use fscanf and fgets to read the file. When it's done reading the file, it's going to use fclose. And we also use, actually, I'm not sure if I use either of these two functions. I think I used them at one point when I wrote this and was testing some things, but then stopped using them. And it's the fact, just the fact that we have gets listed here as an extern function that gives us that warning when we do the LD command. If you remember that, if I go back, here's the linker command. And remember, the linker, when we're building this, is giving this warning right here, that the gets is dangerous to use. It makes it sound kind of scary, but it's just, it's a deprecated function in the C library, basically. It's easy to get buffer overruns. We've learned about buffer overruns, right, with the gets command. So that's basically what they mean by dangerous there. That if you're a programmer writing a serious program and use gets, you're really in danger of letting the user overrun your buffers, and who knows what's going to happen if you let them do that. So, but we're not actually, this program is not actually using get, so you can just delete this line right there, and then you'll never get that warning again. And I think, actually, not sure, I don't think I'm using get car either. Yep, if you do a search, there's only one place where get car shows up, which is right here on the extern. So you can delete that one as well. Not really needed. So these are the only standard C library functions we use. And then you'll notice that we have a whole bunch of ncurses library, which it's supposed to be ncurses, not ncurse. Most of these are things that just need to be used once to just kind of initialize things for ncurses. And there's only one or two that of these that actually get used with any frequency. All right, then we define our global start symbol. And finally you have section text, and the program actually starts. But let's come back up here and look at our data section and BSS section. The data section is very straightforward. It's just a few messages. A couple format strings that the scanfs use, and a format string for a printf to use. All pretty simple stuff, all stuff you've seen before. These are all done as strings, so they all tack on a null terminator at the end. But all pretty straightforward there. There's nothing magical there. We'll probably come back to this BSS section a few times when appropriate for me to explain in more detail. But some of the things to to notice here right off the bat, okay, we have a level file pointer. That's a 4-byte object. That's just a file pointer, just like a file pointer in a C program. Has everyone done file I/O in in their past C programming? Curious of those of you here watching now, has anybody not done file I/O with C programming? Is that yes to you have done it, or no, you have not? I guess say yes or +1 if you have done file I/O. Okay, that's 3 out of 5. Are the other two behind in the video, and so it's going to be a few minutes before they catch up to that question? I'm not sure. But, all right, so at least 3 still. At least 3 of you have done it. That sounds like pretty good odds, at least, that most people have done some file I/O in their C programming. So you know what a file pointer is, hopefully, or you once knew and you can look it up and learn about it. So you may want to refresh your memory on how fgets, fopen, fclose work in C programming if you're a little hazy on that nowadays. And let's see, we have a couple more variables here, level width and level height. And those are just integers that are storing the level width and level height. So if we, again, go back to our file format, when my program reads these two numbers from the level file, it's going to store them right here. Okay? So you may want to, as I'm going through this, you may want to add additional comments in here that I haven't thought to put in. So the width and height we read from the level file will go into these variables, right? Then we have level buffer, and level buffer reserves max level buffer size bytes. And let's find what I set that to. Max level buffer size I set to 2000. You can easily bump it up if you want to play around with large levels. And you know, when you go into your terminal, you can view the zoom out. Whoops, I'd say not zoom in, zoom out, zoom out, zoom out, zoom out. How far can it go? I think that might be the maximum. Nope, can go even further. Even further, wow. Wow, I didn't think it would let me go that far, but you can see how tiny you can make the characters there. So you've actually got a lot of room in these terminals, if you zoom out, that you could have a very large level if you want, and 2,000 bytes would not be big enough to go too much beyond what we have here. So you might want to bump that up if you want to play around with large levels. So, but really, if you just think width times height, plus a new line character at the end of each line, that's the number of bytes you need for a level. So if we look at the file format, take 42 times 20, well, actually, it's going to be 24 lines that are 42 characters long, plus a new line character, so it's going to be 24 times 43 would be the actual number of bytes it needs to represent this level, okay? And that's going to be less than 2,000. That's in the neighborhood of 900 something, I believe. So it only uses about half of the buffer. So you can get a level this big and only use half of those 2,000 bytes that we are setting right here. But if you want a really big level, you're going to need to bump that number up. So the level buffer really is just a buffer, and it's really the whole level is just one big long string. So actually there's one more byte for the null terminator there. So it's a string that has more than one new line character in it, and there's nothing that says there's nothing that says new line characters can't be in the middle of a string, right? So all the lines of the map, of the level map, are all in one big long string. And the length of that string is, the width plus 1 times the height, and then plus 1 to that for the null terminator, is what you're actually putting in there. So that's your level buffer, and that's basically where the map is going to be stored. All the characters, everything that you see displayed while the game is running, that is going to be basically stored in the level buffer. All right, and let's see. And then I've defined level buffer size here for some reason. I don't know if I actually use this. I'm not sure why I did this. I wrote this a year ago, so I can't remember what I was thinking. Since I've already defined the constant here, this and this should end up being equal. I wonder if maybe I change this, since it's in the BS section, maybe when we look at the code, maybe what I do is I reset that to whatever the actual number of bytes used by the level are. But I'm honestly not sure. Maybe I just use one of these and don't use the other one. We'll see. Now the other variables are important to understand, but I'm not going to try to explain them in depth now. But suffice it to say that X step, Y step, and so forth, these start to be used to keep track of the movement of the assemblypede's head and where it moves to, up or down, left or right, and that sort of thing. And then you get this Y delta. All right, actually maybe it is worth explaining. So remember, our level buffer, the thing that actually represents the image of the game, is just a big long string of characters, right? And one thing that's important to know is that if the worm needs to move up or down, if its head's going to move up one line or down one line, well, how many actual bytes in the buffer does that have to jump? And the way to think about that is to go look at the level file. So let's say you're right here. Let's say the head of the worm is right here where I just put this @ sign, and we want to move it right here where I just put that caret, right? So, well, that's going to be however many bytes. You're basically going to be subtracting the address of this byte in the level buffer where the head is. You would have to subtract this many bytes and that many bytes to get to here, basically. I mean, what I just showed you might be off by 1 or 2, because there's a byte for the new line character, and I think we actually need to get all the way to this one, so I think I was probably off by 2. So kind of what I have highlighted here, all these bytes from here to there, and all these bytes from here to there, that's what that Y delta variable represents. So if I want to move this @ sign up, then I need to subtract that many bytes from the address in the level buffer where I want the @ sign to be. If I want to move it down, I have to add that many bytes to move it down to here. Does that make sense? So that's what this Y delta variable is. And if we come through here, okay, then here's a couple variables that are just temporary variables that at certain times in the program will represent the X and Y coordinates of a body segment of the worm. And so we'll see how those are used a little bit more later on. Here's a variable that actually stores the address of the head, of where that @ sign for the assemblypede's head is. So that's basically how we keep track of where it is. Instead of keeping an X and a Y coordinate for that, we're actually just keeping its address in that buffer, and we move it left and right just by adding or subtracting 1. So again, if you want to move the address, the head one step to the right, then you just add 1 to the address of its location in the buffer. And if you want to move it one step to the left, then you subtract 1 from its address in the buffer. But if you want to move it up or down, as we already mentioned, then that's adding a much larger number, however many bytes it takes to fill one line of this text that represents the map. That's the number of bytes you have to subtract to get the new address for the @ sign. Okay, so let's see. So that's an address. Now I also keep track of a thing called a head index and a tail index. I think we will talk about that in more detail later. I'm gonna hold off on trying to explain those. I think I might need to do a diagram to really do that justice. So let's hold off on explaining those. Body length is fairly self-explanatory. It just is how many body segments does it have. And let's see. This debug buffer, I don't think I really use it. I think that's something I had in there when I was developing this program originally, but I don't really use. Let's see if it, oops. Yeah, that's the only place this appears in the program, so this is actually not really used. I think I had something I was doing with it at some point in debugging the program originally, but not really using it. So you could just delete that. Doesn't really need to be there. All right, so that's an overview of the variables. So the only ones I didn't really explain are these three. So I guess I didn't strictly explain the X step and the Y step either, but that's just, each of those is either a -1, 0, or +1, -1, 0, +1, depending on if we are going up, down, left, or right, or standing still. I suppose you could have them both be 1 if you wanted to move diagonally, or -1, 1, 1, -1, -1, or it could be diagonal movement. Currently, the game doesn't support diagonal movement, but I don't know, maybe that's a feature you want to add to the game. So something to think about there. So only these three variables are so far I haven't really explained. So let's actually look at the program itself. So we hit start, and I'm following cdecl even within start here because I want to use command line arguments, and command line arguments are on the stack, so it actually makes sense to save and set the frame pointer. All right, so basically this is saving the initial frame pointer and setting the frame pointer for start. And if you've done it this way, then the command line arguments look like what we are used to, similar to parameters. The one difference is if we look at the cdecl notes, let's jump back to those real quick. You notice that with normal function calls, the first parameter is EBP plus 8. And that's because we have these 4 bytes on the stack for the return address. But at start, there is no return address. Okay? So that first argument, that first parameter, is at EBP plus 4 instead of 8. So again, you know, if you're trying to make sure that you're clear on this stuff, you might want to throw in a comment there. So because there is no return address from start, first parameter at EBP plus 4 instead of EBP plus 8. All right, it's because there is no return address on the stack. All right, so then we have some comments just so you can kind of keep straight what the different arguments are. So, and you can relate these to argc and argv in C. So EBP plus 4, that's argc from C programming. And then each increment of 4 beyond that is a pointer to another character array, which is one of the strings of the arguments themselves. So EBP plus 8 is argv0, and EBP plus 12 is argv1. And for this program, that's the only one we care about because that is the file name of our level file, right? So now I have these 3 instructions, and these are actually kind of in there for debugging. You could probably just delete these. I just was printing out the level file name to make sure it was reading it in, that I was finding it correctly at some point here, and confirming that I had the right level file name. But actually, when it clears the screen to start the game, if you blink, you'll miss this. So it doesn't really have any impact. So you could actually just delete that out of the program if you wanted to, or leave it in because it doesn't really hurt anything. Now, let's see. Now, the first thing we do is we call the load level subroutine. Now, this is a little bit dirty because I'm not really treating this as this is an internal subroutine, so I'm not really treating it as a proper CDECL call. So there's not going to be any business with the stack or anything. So I might as well have put all the instructions for loading up the level file right here at this point in the program, and then just let it continue from there. But I just wanted to kind of get the level process, get all that load level stuff kind of off by itself. And then, so it'll go do that and jump back to this when it's done. But this is not really a proper CDECL call. So call this an internal subroutine, not really a proper CDECL call, okay? But we might as well understand now, since you know what the format is, probably you can understand what this load level is doing. But let's go ahead and jump down there. Oops. So here's the load level routine, and you can see that it actually takes quite a few lines here. Basically goes to, yeah, actually this is part of the load because you have to draw the initial body and so forth. Not a whole lot to wrap up, just returning. So that's pretty much the entire load level routine from there all the way up to still going. There we go. That's the load level routine, which is actually almost half the program. If you look at my mini map of the program off here on the right, you can see all that I just highlighted. That's the load level, which is very nearly half the entire program. Well, maybe closer to a third. So, and if you're not using the mini map, let me go ahead and show you where that is in the preferences. Display overview map right here in the, so from edit preferences, display overview map. And if you haven't, you should definitely experiment with editor preferences here to make your life easier. So at any rate, here's the load level function. Let's see, what do I want to actually talk about this? I think it should be fairly straightforward. So we already know, like, EBP plus 4 is argc and so forth. Oh, the chat screen had it covered up. Oh, let me pull it into view. Let me bring up my monitor here so I can see what you can see. Yeah, I had the virtual machine window a little bit too big, it looks like. There we go. Now you can see my mini map. So here's the mini map over here, and you can even drag the thing that represents the screen to scroll through your program pretty easily. And if I start here and then scroll down to the end of the load level stuff, do shift click, And actually, I think these subroutines are part of the load level as well. So really everything down to the bottom is the load level. So yeah, so that's a good 40% of the program is just load level right here. But yeah, this once your programs start to get long, this mini map of the screen is kind of nice, or of the file is kind of nice. All right, so in load level, I do some basic bulletproofing. So I actually check, do we have exactly one argument? Should be a file name, and if not, we kick out with an error message. So you can see, takes a few steps to get there, but finally we do a comparison to make sure that, oh well, no, right here, we take argc, the count of arguments, put it in edx, compare that to 2, and if it's not equal, we jump to usage. And if you drop down here, usage just makes a call to printf with a usage message that's defined up at the top. And so we do some other things. We attempt to open the file, so we use the fopen library function from C. And again, we check the return address to see if that failed, and then we jump to a routine that prints an error message if that failed. So we jump down here and call another printf message for the failure, and then exit the program. Let's come back up. So it's actually pretty straightforward. You can kind of, I think, based on the comments and everything and knowing what the file format is, now you can kind of walk through this and see everything it does and understand how it's calculating things and so forth. Like the, remember that Y delta, which is how many bytes of address do you have to adjust the address by to go up or down one line in the level map. Well, that's basically calculated from the level width. Actually, it looks like the level width is exactly it. Seems to me that that would be off by 1, but I know my program works, so I must have been right when I wrote this. Oh, no, I increment it right there, so I add 1. So it's level width plus 1. All right, so that's how many bytes you add or subtract to the address of the worm's head to move that @ sign either up one line or down one line in your level map. And so on and so forth. So then we read individual lines of the level map, and I think I have something in here that verifies that those lines are the correct size, but I'm not sure if I actually do that. Let's see. Maybe I don't check. I don't think that amount of bulletproofing may not be in here. Doesn't look like I'm doing a comparison on the length of the lines to make sure they match what was given for the height and the width. So there it's just trusting that the level map file was edited correctly, and if you made one of your lines too long or too short, you're going to see probably a messed up level map. So just keep that in mind. That just means you have to go edit your level file. So at any rate, yeah, I think most of this is pretty straightforward. Maybe the body segments are worth looking at to understand. I would suggest that you kind of go through this stuff where it's loading the body segments, their coordinates, and calculating the address in the level buffer, and make sure that it all makes sense to you. Because that's basically all it's doing. It's reading these coordinates one pair at a time, and then it's figuring out the address. You know, it takes that first pair of coordinates, says, okay, that's where the head is, so now I have to calculate the address in the level buffer where that @ sign needs to go. And then it reads the next pair of coordinates, so, okay, I need to put an O there because that's a body segment, and so forth. Let's see. this might be a good time to talk about the body segment addresses and how that works. So as the level loading program reads these coordinates, it has to figure out the addresses of each body segment, each O, so it can kind of write that into the level buffer. But there is a whole other buffer, a whole other array that's keeping track of all the addresses of all the body segments. Okay? And there's a reason for that. So let's look down here that as we read these things in, okay, let me find where it is here. Yeah, so segment Y and segment X, those we get from reading we have a scanf up here somewhere where we read two integers. Yeah. So here's a scanf where we read, this scanf reads the coordinates of a body segment. Okay. So it's from that we ultimately get segment X and segment Y should get their values. See, we put those as the pointers to the variables where the integers that this scanf is going to read. So segment X and segment Y are the coordinates. Now we use those coordinates to calculate an address. All right. Let's see if I can explain where that is. So that address ultimately ends up right here. Okay. I have this comment one line off because actually it's after this line that EAX now holds the address. So basically what you're seeing here is calculating the address, given the coordinates, calculate the address inside level buffer. So it's basically this address will be the first byte of the level. So if you think about it that way, on this map, it would be the address of that plus sign. That's level buffer. So now we take the Y coordinate and we have to multiply that times the number of bytes per line, basically. That's what the Y delta is. So basically the Y coordinate times number of characters per line, including the new line character. Okay. So for this map that we're looking at, that would be times 43. Okay. And then you just add the X coordinate to that. So if we come over here and want to say, well, what's this? Well, we're on, that's line 0, line 1, line 2 of the map. So that would be a Y coordinate of 2. So you would take 2 times 43 plus 1, 2, 3, 4, or actually I'd say plus 0, 1, 2, 3, 4, 5. So for this location right here, X marks the spot. That would be, you would take the initial buffer address, the address of this byte right here, plus 2 times 43 plus 5 would be the address of that X right there. Okay? So coming back here, that's basically the calculation we're doing here. Now we have to store that. all right, we have to remember the address of the head. We also have to remember the addresses of all the body segments. So we basically kind of have a loop going around here where we read each body segment's coordinate and we store that into, and we calculate its address in the map, and then we store that address in another buffer called body segment addresses. So now let's jump up to the top, and I think now is a good time for me to talk about this, this, and this. All right, so body segment addresses is a buffer of addresses pointing into the map. So I think the best way to do this is to make a diagram. So I'm going to come over to our labs and add this under the thing here, and let's see if I can do this. I can't draw with a pen in this environment, so it might be a little bit rickety. Oh, here's what I'll do. Let's actually, I'm going to grab one of our example level files here. And let's use that kind of as a starting point. So this is our level buffer. Let's actually use the name that is in the program. So body, or let's see, what do we call it? We just call it level buffer. All right, there we go. So using this as an example, we'll just call this the level buffer. All right, and specifically, level buffer is the address of that byte right there. And I don't know why it does these thick lines. Eventually those thick lines turn into thin lines. Those arrows, but we're just going to have fat arrows for a while. Okay, so now the other thing we have is a let's see, I want one column and I want a lot of rows. Let's do like 20. The real one is bigger than this, but just need a table I can work with here for the sake of an example. So I'm going to call this the, and make sure I use the same name we have in the program. This is the body segment addresses array. And each of these is an address of one of the body segments of the worm. Oh, shoot. I'm going to have to edit that and bring a different image over, because I want to actually have some body segments in there, right? So let's bring the level file over, and let me actually say O and O. I think 6 body segments is enough for an example. So there we go. Let me grab that image instead. All right, so level buffer is literally the address of that plus sign there, the first byte in our level buffer. And then each of these we can think of as bytes in the level buffer. So we've organized it for this diagram. It's organized into rows. But you know, I can over here I can say something like this is level buffer plus 43, right? Right there. And notice that my arrow is now skinny over there, but when I draw this one in, I'll bet it'll be fat. And that's the new line character. I shouldn't use black arrows though, because they're gonna be hard to see against the dark background of that image. So that's level buffer 43. Level buffer plus 42 will be the plus sign on the other corner there, right? So now, here's what I want to say, is that at any given time, when the program is running, we're going to have the addresses of the head and all of these O's listed in this body segment addresses array. But I want you to kind of be aware of how this works. So this is sometime in the middle of running the program, not right at the beginning, not right after loading. And now we will have we have those other two variables. We have head index and tail index, okay? And I might as well throw the calculation for those in as well. So, oops. There we go. So let me just put a head index here, and maybe I should use larger fonts for all this text stuff. Make sure it's reasonably readable. Of course, now all my arrows got moved around, but hopefully it's reasonably clear what's going on. All right, so we're sometime in the middle of running the program, and we have body. Let me use the larger version here, so I'm just going to start with this. Make 2 copies of that. So we have body segment addresses plus 4 times head index, I think is what it was called. Let me double check. Yeah, just head index and tail index. And body segment address plus 4 times tail index. So each of these are the calculated address of something in here. So right now my body is 7 segments long, 6 regular segments plus the head. So let me make sure my diagram here matches. Let's say this is pointing to there, and oops, then walk back 1, 2, 3, 4, 5, 6. Wait, 1, 2, 3, 4, 5, 6, 7. So I want to point to that one right there. Okay, and then these addresses are going to be whatever they are, but basically we can think of it as this is the address of where that @ sign is, and this is the address of where the last one is. And let's just, for a complete example, let's at least have one of the middle ones that's easy to point to. So let's go up 2 and say that this one points to that. Okay, so basically this body segment addresses array is storing all the addresses of the head and all the body segments. And then head index and tail index tell you where that starts. Now, what does this mean? Well, think about what happens when it moves. Well, then the head needs to move to a new position. So when we move, I think I want to change pen colors here, but let's use blue, I guess. So when we move, we put the new address here. Okay? And we increment. Did I get head? Oh, I have head index and tail index backwards here. Sorry, folks. We increment head index. So if you were paying attention to which things I wrote there and there, you were probably confused because it should have been tail index up here and head index down there. So yeah, body segment address was 4 times head index. That is this location. And then we store an address in that location, which is the address of where this actual @ sign goes. Okay? And when you move the head by 1, the new location of the head goes in this position. All right? And the new position, and then we increment the head index and we increment the tail index. Okay? And then there's another thing that goes through these, and it starts at tail index, or it actually starts at head index, and it works its way through this address. It puts an @ sign at the position that this is pointing to, so it draws a new @ sign there, and goes all the way through. And then there is one thing that will look at whatever the previous tail index was, it puts a space there, so it erases that O. So that's the essence of what's going on there. All right? Now there's one trick to this, which is this body segment array is not infinite. It only, let's see how big I made it in the program. I think I made it pretty big so that the worm can grow really, really big. In fact, it might be just as big as level buffer size. Yep. In fact, it's that times 4 because each pointer in that array is a 4-byte pointer, right? So to hold that many pointers, it has to be up to max level buffer size. So the worm could actually grow to take up all the space. You know, if it didn't die, it could take up all the space in the entire level because we let it get that size. Now, that's something you could change. You could say there's a maximum size to the worm or something like that. But one of the tricks is, okay, this buffer size is finite. The worm, whether or not it grows, it's going to keep moving. So even if it doesn't grow, it's going to move and move and move. So both, you know, body segment here, that's going to shift, and that's going to shift, and then the position for the new head is going to shift the next clock tick. And each clock tick through this, these things are going to shift with new addresses calculated. The old address is back here. Whoops. The old address is back there. Those are just garbage data now. We're not using them anymore. So there's a part of the program that reads through from the head to the tail in here what addresses those body segments need to be printed to. It makes sure it prints O's, the @ sign and O's in all those positions. Make sure it prints a space in the previous tail address. And that way, at each clock tick, you effectively make the worm move by 1 step. So the trick that comes in here, though, is that let me update all these arrows so that they're in sync with each other, right? So the trick is that what happens when the head index maxes out? What if we only have this many cells in our body segment array, and the head is now pointing there. Well, we can actually use modular arithmetic for all that. So if you pay attention to the arithmetic my program does, it'll just wrap this around back to the beginning. But when it goes through the segments, let me just highlight what could happen here. Let's say it's a much longer worm at the moment, okay? So everything I'm highlighting in purple, from the head back to the tail, is the worm, okay? So you start at the head, but then you subtract 1, but subtracting 1 takes you negative, so you use modular arithmetic, and you go back around to the maximum index in this array, and that's where the address of the first O is, and then the next O, and the next O, and the next O. So it wraps around. So that's one little trick to how this works, and if you're making modifications to how it behaves, you might need to clearly see how this works. Hey, wow, look, my arrow just turned skinny all by itself. I don't know why. That's something to keep in mind. And, oh, darn it, it's not going to let me undo back to previous. So I guess I'm going to go to this, and I'm going to do this. And actually, we might as well put marks down there. So just in general, what's highlighted in green let me do it this way, are addresses of body segments. All right, and I will add to the diagram, calculating the indices uses modulo arithmetic to wrap around once the head index gets too large. Okay, so you can actually have the head index be smaller than the tail index, but you just still do the same thing. You just kind of think of this more like a circle than as a straight line with two ends. Think of it as bending around back to a circle, and then it all makes sense as far as the head index and the tail index. So the head, you go counterclockwise from the head to the tail all the time, no matter which one has the higher numerical value for the head index or the tail index. So hopefully that kind of makes clear. I'm sure some people still have questions, so send me questions and I'll try to clarify it a bit more. But I wanted to walk through it at least once initially so that when you are trying to read the program and understand it, you have a chance. Let's just take a quick look at now what happens in the main program. So we've basically gone over how it loads the file, and then I've explained basically how it uses these variables to keep track of all the body segments and move them around. So now let's actually look at what happens in the program. First of all, we have a bunch of calls to just one time each, basically, to some ncurses functions that initialize things for us. And I've commented each one to give a brief explanation of what they do. You may want to learn more about ncurses because depending on what you want to do, if you get creative, you might want to change how these work. The one that's really important here is this timeout. So this is an ncurses function that sets a timeout on an input function that reads a single character. So normally in C programming, if you ever use like the getChar or the getCh function that reads just one character, it doesn't wait. It's gonna read a character, but if there's nothing available, Yeah, well, let me phrase that better. It's going to wait as long as it takes for the user to type something to read that character. It's just going to wait forever. If the user never types a character and presses turn, it doesn't care. It'll sit there and wait. But there is an ncurses function that has a timeout, so you can set it to only wait a fraction of a second for the user. And if that passes, then you say the user hasn't done any input, so now we can let the game clock tick once more, and the game can update. That way the worm keeps moving. Even if the user doesn't press a key, the worm is just going to keep going whatever direction. So that puts pressure on the user because it's going to hit a wall and die or something, so they have to turn and avoid having the worm crash into something. So, so it makes timing important. Now, the way this is written, it's written in a very simple way, and there's a couple weird things where the timing is not always consistent. If the user hits the keys really fast, they can make the clock go faster, basically. Because if the user presses it, if it's waiting a quarter second, but the user presses the key in a tenth of a second, well, that's all the time it's going to take to read that key. There's not anything in here that forces the clock tick to be consistent in that sense. Again, if you don't like that and you want to figure out how to tweak it to make it have a consistent clock tick, that would be something fun that you might try and work out. It's not terribly hard to do that, but it just, it's another level of complexity. I didn't want to make this program too complex to understand. But, okay, down here is the main game loop, and the first thing we do is clear the screen. The second thing we do is we're basically printing the entire level buffer. That's just one big string, and we use a print function. This is print W from ncurses, so it's not printf, it's print W. And you can Google ncurses and learn a little bit more about exactly how that works if you need to. Otherwise, just suffice it. What we're doing here by clearing and doing a print W, that's going to start the printing from the top left corner and print the whole thing, and so it reprints the map. So basically, each time through the game loop, we reprint the map. So that's one tick of the game clock. Then I have this subroutine called game tick, and we jump to that, and that basically takes care of seeing, did the user press a key, and how does the worm move, did we crash into a wall, that sort of thing. So most of what you want to do, most of the action of the game gets taken care of in this game tick. And then it's kind of an infinite loop here, jumping back to game loop. So this is the essence of it. That's your game. It just, each time through this section of the code, that's one tick of the game clock right there. All right. So now what happens in game tick? Let's jump down there. Well, the very first thing is we call this getCH function. This is an ncurses input function, and it works with that timeout. So it's a combination of setting a timeout and using this function allows us to see what the user enters, but we don't wait very long. And if the user takes more than a tenth of a second or a quarter of a second or whatever we choose, then we just let the game clock tick again and update the screen, and then come back around and we check and see if the user's pressed anything. Then, okay, now we just have a bunch of simple things. We take what the user entered and compare that to different letters. So one of the things you'll find is this getCH. It has a return value. That return value returns the ASCII code of the key that was pressed right there. And we can just compare it right there. It puts it in EAX, but it's just 1 byte, so it's actually in AL. So we compare that to the different keys we're looking for. So here we're looking at WASD. So, one of the things you're supposed to do in the instructions is you'll let the space bar pause the game, right? So over here in the program, that's a place where you would want to compare to spacebar, and then you would jump to the section that takes care of pausing the game. That sort of thing. So now you can kind of see, okay, if they press W, that means we want to go up, but notice that the worm will keep going in the same direction. So I only have to press W once to start it going up, and then if I don't press any other keys, it'll just keep going up. So what happens here is it sets the variables for X step and Y step to indicate what direction it's moving. So the keys change the direction, they don't actually cause it to move. So whatever key they pressed, we then just change X step and Y step to indicate what direction they're moving. So if they did an up with a W, then we set X step to 0 because they're not moving side to side. X is side to side, left and right. Y is up and down. So the Y step is set to -1. Remember, we count the Y coordinate from the top. So the top is 0, then it's 1, 2, 3, 4. So if you want to go up by one line, you would subtract 1 from the Y coordinate. So so having X step of 0 and Y step of -1 means we've set the direction of movement up. All right? And similarly for the other keys. Let's see. And then whichever key we handle, then we jump to this continue. And then here's the stuff that calculates the new position of the head, the new position of the tail, updates those body segment addresses. So the stuff that we diagrammed over here and how the tail index and head index shift, that's all taken care of now in this section of the program. And so that's pretty much everything from there to there. So I think we're hitting right on our time limit here, and I think I've pretty well given you a pretty solid overview. I'm going to leave it a little bit more as on you to kind of sort through this, given the explanation that you've already had. Now actually read this code and see how it matches up with what I explained. Okay, so once you understand how the program works, then you can start thinking about, okay, how do I modify this program to do what it needs to do? Just one more piece of overview on that. You know, what's one of the other things I said you're going to need to do? When it eats a bit of food, it needs to grow. Well, what does that mean? Well, that probably means that the head index needs to go up by 1, but the tail index stays the same. That way they become one more byte or one more step apart from each other, right? So right now here you see there's 7 body segments in this example. So if it eats an asterisk, if it runs over an asterisk and eats that bit of food, then you would let the head index go up by 1, but you would not let the tail index go up by 1. And that lets it grow. And you would not put a space where the last tail was, where the tail was. You would let that still be an O. So that's how that works. Let's see. Is there anything else I want to say before I call an end to this? Yeah, I think that's about it. Yeah, so everything here from here down takes care of updating the body segment address array, the tail index and head index, and it takes care of changing the values of things here in the level buffer. So it'll change an O to a space if the tail needs to move. It'll change the head, it'll change the @ sign to an O, and then put the @ sign in the next position if the head moved. And the head always moves. In this game, it's not allowed to stop. You have to keep moving. Now, again, you're free to come up with new features of the game. So if you want a game where the worm can stop moving, more power to you. See if you can make an interesting game idea out of that and work with it. Certainly we do stop it when we hit pause, but that's not really, but that's because we're pausing the whole game. So at any rate, there's your overview of how that program works. Hopefully that's enough for you to get started. When you dig into it, run into questions, certainly email me with additional questions. Try not to procrastinate, because you are probably going to get confused by things and you want to have time to ask questions or to solve them for yourself or whatever. All right. Let's see. Oh, shoot. I haven't had the chat up for a while, so if anybody has been chiming in with a question right now, I haven't seen it. Doesn't look like anybody was asking questions. So I'm going to pause just for a moment here and let people catch up in the video and see if anybody wants to ask anything right now. If not, that'll be it for tonight. You can, but it looks like I kind of burned up time. Let's, but I'll go ahead and stick around a little bit. So yeah, you have a question about Lab 7? That's fine too. If you think it's fairly specific to you, great. If you think that every others can benefit from it, we could, well, I don't know, if I would send a thing out or add a tip to the instructions. So yeah, just go ahead and email me, because yeah, you can always ask questions about all the labs. I'm happy to answer questions. So does anybody have any questions about what's expected for the final project? All right, I'm just now realizing that the mic is picking up my drumming here. And now my drumming is getting thrown way off because I'm self-conscious about it. All right, doesn't look like anybody has any other questions. Thank you and good night, and until next time.